Welcome to the Deep Dive, the show that, well, aims to cut through all the noise and get you straight to the insights. We really want to give you that shortcut to being genuinely well-informed, packed with surprising facts, and hopefully just enough humor to keep you hooked along the way. Today, we're plunging into the fascinating and sometimes, let's be honest, bewildering world of deep learning.
Oh, yeah. Definitely bewildering at times.
Right. But this field has, without a doubt, brought us some of the most incredible capabilities we've seen. Things like recognizing faces in photos, powering chatbots that sound almost human.
The progress has been staggering. Natural language processing, computer vision, it's everywhere now.
These are genuinely phenomenal breakthroughs, really pushing the boundaries of what we thought AI could even do. But like with any cutting-edge tech, there's always a flip side, isn't there? A sort of hidden struggle. Training these incredibly complex, deep networks, well, it hasn't always been easy.
Not at all. For a long time, it was a real headache.
Researchers faced, notoriously increased training complexity. You had to be incredibly careful just initializing the weights to even get started.
Yeah, that initial setup was crucial. Get it wrong and disaster.
And you often needed these painfully low learning rates just to stop everything from, well, exploding.
Right. It felt like walking a tightrope. Too slow, it takes forever. Too fast, it just diverges.
It really felt like there was this invisible wall, almost like a prohibition, as some put it, that limited how deep we could actually make our networks without them just refusing to learn.
That's a good way to put it. There was a practical limit.
And then along came a true hero in this story, a really prominent innovation that just fundamentally changed the game. Batch normalization, or BN.
Ah, yes. BN. The star of today's show.
It was such a game changer. It absolutely lifted that prohibition, suddenly allowing researchers, engineers, everyone to explore much deeper, much more intricate network architectures than ever before.
It really did open the floodgates. Suddenly, these super deep models became practical.
So what exactly is batch normalization on a surface level?
Okay, so at its core, it's actually quite an elegant concept, but its effect is huge. What BN does is it normalizes the intermediate activations within the network.
Normalizes how?
Basically, for each layer, it makes sure the inputs going into the activation function have, on average, 0 mean and unit standard deviation. It standardizes things within each mini batch of data during training.
Okay, so keeping things consistent layer to layer.
Exactly. Think of it like ensuring a stable, predictable flow. But then, crucially, it also introduces two trainable variables. We call them gamma and beta.
Trainable. So the network learns them.
Precisely. Gamma is for scaling and beta is for shifting. So after standardizing, the network can either learn, maybe for this task, I actually need a slightly different mean or variance here. It gives back some flexibility.
Ah, I see. So it standardizes, but doesn't lock things down completely. It allows learned adjustments.
You got it. It normalizes for stability, but preserves the network's expressive power. It's quite clever.
And the impact was? Well, it's still massive, right? BN is everywhere now.
Oh, absolutely. It's pretty much considered essential in most deep learning models. It dramatically accelerates training, makes things feasible that just weren't before.
But here's the kicker, the interesting part for today. For years, even though everyone knew it worked wonders, the exact theoretical reason why it was so successful, that's been a hot topic.
Lots of research, lots of debate. We knew it worked, but the deep why was still a bit fuzzy, a puzzle.
All right, let's unpack this then. Because today, we're diving into a really groundbreaking paper that seems to have found a hidden, almost secret superpower of batch normalization. Something that goes way beyond what we thought we knew.
Yeah, this is really exciting stuff. This deep dive will basically show that BN isn't just speeding things up, it's actually performing this data-dependent auto-tuning of the regularization parameter.
Okay, hold on. Regularization. That's the thing that stops models from overfitting, right? Memorizing the training data instead of learning general patterns.
Exactly that. Crucial for making models work on new data. And normally, finding the right amount of regularization, that's a manual job. A hyperparameter you have to tune, often through painful trial and error.
And you're saying BN does this automatically.
That's what the paper argues and provides evidence for. It suggests BN handles this intelligently, adapting the regularization based on the data it sees.
Wow. Okay. So prepare for some genuine aha moments, folks, as we uncover just how much smarter batch normalization might be than we ever realized. This sounds like more than just faster training.
It really points towards a kind of built-in intelligence.
So let's dig a bit deeper into what BN is. We said it's like an additional layer you add.
Yeah, you can think of it like that. A specialized module that slots into your network, usually right before the activation function in a layer.
And its main job is normalizing those inputs using batch statistics,
Mm.
nu and sigma.
Right. Kuzo for mean, for Nisbo. For the standard deviation, these are calculated dynamically from the current mini batch of data flowing through during training, so it adapts constantly to the data it's seeing right now.
Okay, so it's always adjusting based on the immediate data context.
Precisely. It ensures that, statistically speaking, the inputs to the activation functions are consistently scaled and centered, which helps prevent those wild fluctuations that can derail training in deep networks.
And those trainable parameters, gamma and beta you mentioned, how critical are they again?
Oh, they're absolutely critical. EVO is the scaling factor, LVO is the shifting factor.
Yeah.
Think about it. DAN first forces the inputs to have zero mean and unit variance. But maybe, just maybe, the optimal input distribution for a specific activation function in this particular network isn't exactly zero mean unit variance.
Ah, okay, so the network might actually want something slightly different.
Exactly. Maybe a real U activation works best if its inputs are slightly shifted, or maybe a sigmoid needs inputs with a different variance. Gamma and beta allow the network to learn these optimal adjustments. It learns to scale and shift the normalized values.
So it gets the stability benefits of normalization, but doesn't lose the ability to represent complex functions.
You nailed it. It gets stability and flexibility. It's a really elegant balance.
We need a good analogy here.
Yeah.
How should people picture this?
Okay, try this. Imagine batch normalization as like a super diligent quality control inspector working on a complex factory assembly line.
Okay, like it.
So as each component, that's our activation input, moves from one stage of the factory, one layer of the network to the next, this inspector steps in.
So this job?
Their job is to meticulously check every component against strict standards. Does it have the right average size? That's our zero mean. Is the variability consistent? That's our unit standard deviation. Only components meeting these specs are allowed to move on.
And why is that so important on the assembly line?
Well, imagine if components started drifting slightly out of spec early on. By the time they get further down the line, those small errors could accumulate, causing major jams, breakdowns, inefficiencies, chaos.
Right, a cascade effect.
Exactly. BN, our inspector, prevents that cascade. It ensures every stage, every layer, receives inputs that are predictable and consistent. This lets the whole system run much more smoothly and efficiently. It drastically reduces the chance of the whole process just grinding to a halt.
That's a fantastic analogy.
Right.
It really helps visualize the stability aspect. And that kind of stability. It wasn't just nice to have, it became indispensable, didn't it? Thinking back to before BN.
Oh, absolutely. That pre-BN era, training really deep networks felt, like you said, almost impossible. That prohibition wasn't a rule, but a practical reality.
The challenges were just immense. Increased training complexity,
Everything was harder.
that need for incredibly careful, almost surgical weight initialization.
Yep. Tiny changes could have huge impacts.
And sticking to those agonizingly low learning rates.
Because anything faster would just cause things to explode or vanish. It was a constant battle against instability.
So BN just bulldozed those problems.
In a way, yes. By standardizing activations doing that quality control, it smoothed out what we call the optimization landscape. It made the path to finding the best weights much less treacherous.
Easier for the optimizer to navigate.
Much easier, more stable. This meant you could train faster, deeper. It dramatically accelerated the training process for these very deep networks. It wasn't just a small tweak, it was a paradigm shift.
And that's why it became so essential.
Totally. It became a cornerstone for pushing the frontiers, especially in convolutional neural networks. Think about things like ResNets, inception networks. BN was a key enabler for those breakthroughs.
And now it's just fundamental across so many applications.
Computer vision, NLP, reinforcement learning, you name it. BN made deep learning practical and performant for a much wider range of complex tasks.
Now, it's fair to say BN wasn't the only idea for normalization floating around at the time, right? People were trying other things.
Oh, definitely. It was a hot research area around, say, the mid-2010s. Everyone was grappling with how to stabilize these deeper models. BN just happened to be particularly effective and caught on quickly.
What were some of those other ideas?
Well, you had a whole family of what are sometimes called orthogonal normalizers, techniques aiming for similar goals but using different methods. There was layer normalization.
How's that different?
Layer normalizes across the features within a single data sample, not across the batch. Then there was instance normalization, which became popular in style transfer for images.
Yeah.
You also had things like divisive normalization, group normalization, which splits channels into groups for normalization, and even weight normalization, which tackles the weights directly instead of the activations.
So lots of different approaches.
Yeah, and there were even researchers trying to figure out how to train deep networks without any normalization at all, using other tricks.
But BN seems to have stuck around more than most.
It really has. Despite all those other efforts, all the alternatives, batch normalization still stands out as a kind of milestone technique. Its performance boosts, its reliability in speeding up training, and often improving generalization. It's just consistently delivered.
Which brings us back to the mystery. Why? If it works so well, surely people figured out the exact theoretical reasons.
Well, they certainly tried. For a long time, researchers have been trying to pin down the precise reasons for BN's success. It worked, but the how and why at a deep theoretical level was elusive. Lots of hypotheses flew around.
What were the main contenders? The leading theories?
Okay, so the explanations generally fell into a few buckets. One big one was optimization improvements. The idea was that BN somehow makes the process of finding the best weights easier for the optimizer.
How so?
Some early work, famously, proposed it worked by reducing internal covariance shift. That's the idea that the distribution of activations inside the network keeps changing as training progresses, making it hard for later layers to adapt, like trying to hit a moving target.
Okay, that sounds plausible.
It did, but later research kind of poked holes in that being the primary reason. More recent work suggests it's less about fixing that specific shift and more about generally smoothing the loss landscape.
Smoothing the landscape, like making the path to the solution less bumpy.
Exactly. And also increasing the stability of the loss function, partly by reducing something called the loss Hessian. Basically, it makes the optimization problem itself better behaved, allowing the optimizer to take bigger, more confident steps without falling off a cliff.
Okay, so better optimization dynamics. What else?
Another popular explanation was that BN allows for larger learning rates. This was consistently observed in practice.
And why would that be good? Isn't faster sometimes riskier?
It can be, but the argument was twofold. First, higher learning rates can introduce a bit more randomness or noise into the optimization process, which can sometimes help the network avoid getting stuck in bad local minima and find solutions that generalize better.
A bit counterintuitive, but okay.
And second, BN prevents what's called activation overgrowth deep in the network. Without BN, high learning rates can cause activations to explode, leading to instability. BN keeps them in check, allowing for those faster learning rates without the network going haywire.
Got it. Stable enough for speed. Any other theories?
Yep. Another angle was weight scale invariance. The idea here is that BN makes the network kind of immune to the overall scale of the weights in a layer.
Meaning if you doubled all the weights, BN would cancel it out.
Essentially, yes. The normalization step adjusts for that scaling. This helps because the optimizer can focus on learning the direction of the weights, which is often more important than their exact magnitude, making learning more stable.
Interesting. Decoupling magnitude and direction.
And finally, some researchers suggested BN provided a form of explicit regularization, even if implicitly.
How does that work?
The thinking was that BN encourages all neurons in a layer to participate, rather than letting a few dominate. It might also reduce the peakedness, kurtosis of the input distribution, and decrease correlation between neurons. These effects could act like built-in regularization, discouraging overfitting.
Okay, so optimization help, bigger learning rates, weight scale invariance, maybe some implicit regularization. BN was already seen as doing a lot of good things.
Absolutely. It was already understood as this multifaceted tool, a real Swiss Army knife for training deep networks.
But you're saying the paper we're looking at today found something else, something even deeper.
That's right. Despite all those valuable insights, there was still a crucial piece missing, a fundamental theoretical gap in fully explaining BN's magic.
And this is where it gets really interesting. So this hidden superpower. What exactly was the missing piece that this new paper claims to have found? What did all those other theories overlook?
Great question. It boils down to this. Despite everyone acknowledging BN helps with the generalization, how well the model works on new data, there was no clear analytical mathematical link showing how BN directly affects the regularization parameter itself.
Ah, okay. So people suspected it helped generalization, maybe through those implicit effects you mentioned, but couldn't mathematically prove it was tuning the regularization.
Exactly. There wasn't a formula saying, here's how BN determines the regularization strength. That connection, that direct analytical relationship between BN's operation and the regularization rate was the missing link. This paper argues it found that link.
And that's a big deal because regularization is so fundamental, right? We should probably quickly recap why it matters so much.
Absolutely. Regularization is key. Imagine you're studying for that big exam again.
Okay, exam time.
You don't want to just memorize the answers to the practice questions, right? Because the real exam might have different questions. You want to understand the concepts.
Right, so I can tackle anything they throw at me.
Exactly. Regularization is like that for a deep learning model. It pushes the model to learn the underlying concepts, the general patterns in the data, rather than just memorizing the specific training examples, noise, and all.
Because memorizing leads to overfitting.
Precisely. Overfitting is when your model aces the practice questions, training data, but bombs the real exam, new, unseen data. It hasn't truly learned, it just memorized. Regularization is our main weapon against that.
And finding the right amount of regularization, the rate, that's the tricky part.
Oh, yeah. It's crucial. You need enough complexity to capture the real patterns, but not so much that you start modeling the noise. It's this delicate balance between model simplicity and fitting the training data well.
Finding that sweet spot sounds hard.
It is, because the ideal regularization rate is highly data dependent. It changes based on the data set, the model architecture, even the specific task.
So how do people normally find it?
Traditionally, it's a lot of trial and error. The most common method is cross-validation. You basically train the model many times with different regularization rates, see which one performs best on a held-out validation set, and pick that one.
That sounds tedious
And
expensive.
extremely. It's often a manual, iterative process that can burn through huge amounts of computational resources and developer time, weeks sometimes, just tuning this one hyperparameter.
Wow. Okay, so the paper's claim is that BN basically automates this whole painful process.
That's the revolutionary idea. The paper argues that BN effectively estimates the optimal regularization rate needed for the non-BN weights directly from the data itself during training.
So it removed the need for manual tuning of that regularization parameter.
That's the implication. It suggests BN is intelligently handling a significant part of the regularization puzzle automatically. Think about the efficiency gain. Less human guesswork, less computational cost wasted on endless tuning experiments.
It's like having an expert tuner built right into the network.
Kind of, yeah. Imagine, instead of you manually fiddling with that strictness knob for regularization, BN is constantly intelligently adjusting it based on the statistics of the data it's processing in real time, an adaptive coach for generalization.
That's huge. And you said the paper shows this from two different angles.
Correct. They present two complementary perspectives to build their case. First, they frame BN as a constrained optimization problem. They show mathematically how solving this inherent optimization leads directly to data-dependent regularization.
Okay, a mathematical proof route.
And second, they analyze how BN behaves when the input data is noisy. This reveals how BN dynamically tunes the regularization based on the balance between the actual information, the signal, and the random interference, the noise.
Signal versus noise tuning.
Yep.
Okay, two distinct but converging lines of argument. Let's dive into the first one, the optimization angle. Okay, so to really get our heads around this theory, the paper smartly starts simple, right? Looking at BN in just a single perceptron, the most basic unit of a neural network.
Exactly. It's much easier to see the mechanics without the complexity of many layers interacting. So for one perceptron, the BN calculation is y equals x BRJ x TW weight.
Let's break that down again quickly. X is input, W is weight.
Y is the output after BN, and are the batch mean and standard deviation of the pre-activation XTW. And X and IC are those learned scale and shift parameters.
Got it.
Now, to make the math cleaner for the theoretical derivation, they make a couple of standard assumptions. They assume the input X has zero mean, which is common practice anyway, and they temporarily ignore B, the shift parameter, because the core regularization effect comes from the scaling part.
Okay, simplifying assumptions.
With those, the equation becomes Y XTW WTRW12. Now, this R here is important. It's the covariance matrix of the input X.
Covariance matrix.
Yeah.
What does that represent intuitively?
Think of R as capturing the statistical structure of your input data. How different features vary together, their correlations. It's like a summary of the data's shape. The term WTR W12 essentially represents the standard deviation of the projection XTW, taking into account this data structure.
Okay, so the denominator is like a structured standard deviation.
You could think of it that way. And this form lets us define an effective weight vector, let's call it WBN. We can rewrite the output simply as y equals xt WBN.
And what is this WBN?
WBN is equal to WTR WTR12. This WBN represents the weight vector after the BN transformation has been implicitly applied. It's how BN effectively modifies the raw weight W.
Okay, so WBN includes the BN effect. Now, the paper says BN isn't just doing this calculation, it's doing it because it's trying to achieve some goal, an optimality criterion.
That's the core theoretical proposal. They argue BN operates as if it's trying to solve a specific optimization problem. The goal is minimize a weighted norm of this effective weight WBN while keeping the projection of WBN back onto the original weight W fixed.
Okay, minimize something, subject to a constraint. What's the constraint mathematically?
The constraint is WBNT W equals 1.
WBN projected onto W equals 1. Why is that constraint so important?
It's absolutely vital. This constraint ensures that the fundamental direction learned by the original weight W is preserved. It means BN can apply its normalization and regularization without distorting the core information the neuron is trying to capture. It keeps the learning signal intact while enhancing stability and generalization.
So it regulates without damaging the learned pattern.
Precisely. And the term being minimized is EWT by 212, WBNT, WBN. This part, this minimization target, acts as the regularization function. It's penalizing the magnitude or complexity of the effective VN weights.
Okay, so BN is implicitly minimizing this term, subject to that projection constraint. How does this lead to auto-tuning regularization?
This is where the math gets elegant. They use the method of Lagrange multipliers, a standard technique for solving these kinds of constrained optimization problems, to find the optimal form of WBN.
And what do they find?
They found that the optimal WBN that satisfies this minimization under constraint is WBN ERB MPO WTR W12.
Wait, that looks almost identical to the WBN definition from before.
It does, but the key insight comes from identifying what IB is. The Lagrange multiplier method directly shows that this OB term, which acts like a scaling factor, or effectively the regularization strength, is equal to EWT by 212.
Okay. EWT by 212. What is that?
Remember, WTX is the neuron's pre-activation signal. WT by 2 is its squared magnitude. E means the expected value or average over the data. So EWT by 212 is essentially the root mean square RMS magnitude of the neuron's activation signal.
The average strength of the neuron's response.
Kind of, yeah. And here's the kicker. The derivation also shows that this OB is equal to BN's own trainable scaling parameter.
Oh, so the regularization strength OB is the learned gamma parameter.
Yes. This is the magic. The paper demonstrates that the regularization rate isn't some fixed value you set manually. It is gamma, and gamma is dynamically estimated by BN itself, based on the RMS activation strength EWT by 212, which depends directly on the weights W and the data statistics R.
So BN is literally learning the regularization rate via gamma based on how strongly the neuron responds to the data.
That's exactly the claim. The regularization is data-dependent and adaptive, tuned automatically by the network during training.
Okay, let's unpack how this adaptation works. You said IA, or gamma, depends on EWT by 212. What happens if WTX, the neuron's activation signal, is generally high?
If WTX is high on average, it means the neuron is responding strongly to the inputs. In this situation, as we discussed, even small input noise or perturbations can cause large output variations. The neuron is sensitive, potentially unstable.
Right, prone to overreacting.
So BN intelligently mitigates this. If EWT by 212 is high, then IA gamma will also be high. According to the optimization framework, a higher I corresponds to stronger regularization.
Ah, so if the neuron is highly active and sensitive, BN automatically increases the regularization penalty to make it more robust.
Precisely. It's a proportional relationship. Stronger activation leads to stronger regularization. It's a beautiful self-correcting mechanism baked right into BN.
And does this connect to generalization?
Absolutely. The paper argues this improves generalization by creating this proportional link between the regularization and factors like the weight magnitude, W, input magnitude X, and their alignment. It means regularization isn't applied blindly.
How so?
For instance, if data points are near the decision boundary, ambiguous cases, the activation WTX might be relatively low. BN would then apply less regularization, allowing the neuron to make those fine distinctions without being overly smoothed out. It adapts the intensity based on the context.
That makes sense. Don't regularize away the important details.
Right. And there's another key finding related to the overall data variance, SUX. The paper shows that as data variance increases, the network naturally tends to memorize less.
Because the data is more varied, harder to just memorize.
Exactly. And BN mirrors this. The derived regularization, EBN, is shown to be proportional to this data variance, IBN against 2x. So if the data itself is inherently noisy or diverse, making overfitting less likely anyway, BN automatically dials back the regularization strength.
So it's adapting not just to neuron activity, but also to the inherent noisiness or diversity of the data itself.
Yes. It's remarkably sophisticated. It tunes regularization based on both the neuron's state and the data's statistical properties.
Okay, that constrained optimization view is really compelling. It gives a solid mathematical basis for BN's auto-tuning. Now let's look at the second perspective the paper offers, how BN behaves with noisy input data. This feels very relevant because real-world data is almost never perfectly clean, right?
Absolutely. Noise is everywhere. Sensor noise, measurement errors, inherent variability. So understanding how BN handles it is crucial.
How did the researchers model this?
They use a pretty standard approach. They imagined the input data X being corrupted by some additive Gaussian noise, let's call it ASCO. So the network doesn't see the true input X, it sees a noisy version, XN, oils X plus X.
And this noise X is just random interference.
Yeah, specifically Gaussian noise, meaning it follows that familiar bell curve shape. It has a mean of 0, so it doesn't systematically shift the data, and some variance, let's say S2, which represents the amount or power of the noise.
Okay, so they feed this noisy XN into the model. What were they looking for?
They wanted to analyze the impact of this noise on the model's error, specifically the mean square error, MSE, between the output predicted from the noisy input, high error, and the output you'd get from the true, clean input, Y, so Ekanian Y2.
And what did they find happens to the error when noise is present?
Their analysis showed something really neat. The MSE with noisy input naturally includes an additional term compared to the error with clean input, and this extra term is proportional to 2, the variance of the noise itself.
So the noise itself adds a kind of penalty term to the error.
Effectively, yes. This mathematically confirms the intuition that noise inherently acts as a form of regularization. It makes the data harder to fit perfectly, discouraging the model from memorizing the noise along with the signal.
Okay, noise is a natural regularizer. How does BN interact with this?
This is where it gets really interesting. They took their expression for the effective BN weight, WBN, which we know incorporates gamma and the data covariance R, and substituted it into this MSE equation that includes the noise term.
Plugging the BN mechanism into the noisy error calculation.
Exactly. Then, after some mathematical simplification, including assuming, for clarity, that the eigenvalues OJ of the data covariance matrix R are roughly equal, let's just call this average eigenvalue O.
What does O represent here?
Think of O as representing the variance or the overall strength of the true signal in the data. It's related to the eigenvalues of the covariance matrix R.
Okay, so O is signal strength, 2 is noise strength. What did the math show?
After the substitutions and simplifications, they found that the effective regularization parameter in this noisy scenario becomes Starko plus 2.
Okay, that expression looks important. What does it tell us? This must be the aha moment for the noise perspective.
It absolutely is. Let's look at the extremes to understand its behavior. First, what happens if the noise is way stronger than the signal? So Starko is much, much bigger than the signal.
Then in the denominator, stucco plus 2 is tiny compared to stuck. So the denominator is basically just sucso.
Right, and the whole expression stucco plus 2 simplifies to approximately stucco 2, which is just stuck 2.
So in very high noise, the regularization approaches 2.
Exactly. BN applies a significant amount of regularization, primarily determined by its learned gamma parameter. This makes sense. When the input is mostly noise, you want strong regularization to stop the model learning garbage.
Okay, that checks out. Now what about the other extreme? Very strong signal, very little noise. So ALCO is much, much bigger than...
Now, in the denominator, the STU term is negligible compared to O. So the denominator is basically just O.
And the expression STU to O plus 2 becomes approximately 2 plus 2.
Let's recheck that logic. If US2, then O plus 2 O. The regularization term is US2 plus 2. Oh, wait. Let's reconsider the interpretation. The derivation links this term to the overall regularization effect. The key insight is how the effective regularization changes relative to signal and noise. The paper actually highlights the inverse relationship with signal variance. When signal is high, the need for regularization might decrease. Let me rephrase the core finding.
Okay, take your time. It's subtle math.
Right. The crucial point they emphasize is this. BO makes the regularization parameter inversely proportional to the signal variance.
Inversely proportional to signal variance, meaning
Meaning, when the variance of the true signal is high, if the underlying data patterns are inherently very diverse or complex, the model finds it harder to just memorize the data anyway.
because the signal itself isn't simple or repetitive.
Exactly. In such cases, the need for additional explicit regularization is lower. And BN automatically achieves this. By having the effective regularization inversely related to BN naturally reduces the regularization strength when the signal variance is already high.
So if the signal is complex and hard to memorize, BN says, okay, I don't need to clamp down so hard.
Precisely. Conversely, if the signal variance is low, meaning the signal is very consistent, perhaps easier to memorize, BN would implicitly increase the relative regularization effect to prevent that memorization. It adapts based on the signal's own characteristics.
It's tuning based on the signal-to-noise ratio, SNR, in a really smart way.
Yes. It automatically tunes the regularization based on both the signal variance and the noise variance.
Huh.
If noise dominates, it regularizes strongly. If the signal is strong and complex, it eases off. If the signal is strong but simple, it regularizes more.
That's incredible. It's like BN has this built-in adaptive filter. It's constantly assessing the quality of the incoming information, separating signal from noise, and adjusting its learning style, its regularization strength, accordingly.
It's a very powerful interpretation. It suggests BN isn't just normalizing, it's actively performing signal processing to optimize learning and generalization in the face of noise.
For anyone dealing with real-world, messy data, having this automatic adaptation built in, that seems like a massive advantage. Less fiddling for us.
Absolutely. It makes models inherently more robust to varying data quality without manual intervention.
Okay, so we've got these two really elegant theoretical arguments, constrained optimization and noise adaptation, both pointing to BN as this automatic regularization tuner. But theory is one thing. Did the researchers actually test this in practice? Did they run experiments?
Oh, absolutely. Good science demands empirical validation. They designed experiments specifically to see if the real-world behavior of BN matched these theoretical predictions. Time to see if the math holds up.
What was their experimental setup? Did they use complex, state-of-the-art models?
Actually, no, they kept it deliberately simple to isolate the effect of BN. They used a basic multi-layer perceptron, an MLP, just a standard feed-forward neural network.
Why simple?
Because using something like a giant ResNet introduces lots of other complexities, skip connections, different layer types. A simple MLP lets you see the impact of BN more clearly without other factors muddying the waters.
Makes sense. And what data did they use?
They use the classic MICE dataset, the handwritten digits dataset. It's a standard benchmark, well understood, good for demonstrating fundamental principles.
Okay, so a simple MLP on MNIST. Can you describe the network structure a bit more?
Sure, it was pretty shallow. Just one hidden layer with 300 nodes using the standard ReLU activation function. Then that fed into a final output layer with 10 nodes, one for each digit, 0 through 9, using softmax activation to get probabilities.
And where did BN fit in?
Crucially, they applied batch normalization right after each dense layer, so both after the input to hidden layer and after the hidden to output layer, just before the activation functions.
Standard placement. And the training details.
They used a batch size of 128, categorical cross-entropy loss, standard for multi-class classification like MNIST, the atom optimizer with a learning rate of 0.1, and small random initial weights.
And the goal wasn't just to get the best possible score on MNIST.
Exactly. The goal wasn't state-of-the-art accuracy. It was specifically to test the hypothesis about BN's data-dependent regularization. Does it actually behave the way the theory predicts?
Okay, let's get to the first experiment. This one was testing the idea from the constrained optimization part that e do t by 212 thing acts as the regularization parameter on E. How did they test that?
It was quite clever. They needed a way to manipulate that e do t by 212 term, which represents the RMS activation strength. Instead of messing with weights directly, they manipulated the input data x. They simply applied a scaling factor to the input MNIST images, varying this factor from 2 up to 6, so making the pixel values and thus the input signals x stronger overall.
Ah, so Increasing the data amplitude should increase EDOT by 212 and therefore increase the predicted regularization INVA.
That was the prediction. Then they measured what actually happened to the network's weights, specifically looking at the L1 norm and L2 norm of the weight vectors in the hidden layer.
Remind us what lower norms mean again.
Lower weight norms, L1 or L2, mean the weights are smaller in magnitude, which indicates stronger regularization is being applied. The model is being penalized more for having large weights. They also calculated their theoretical OR based on the observed activations.
So did the results line up? Did scaling the data change the regularization?
The results shown in Table R of the paper were incredibly clear. As they increased the data scaling factor from 2 to 6, the estimated regularization rate, calculated from the activations, increased dramatically almost tenfold, from about 0.92 by 108 to 8.3 by 108.
Wow, okay. So the predicted regularization intensity went way up. What happened to the actual weight norms?
Exactly as the theory predicted. Concurrently, the mean L1 norm of the weights decreased significantly from 0.7210 down to 0.0793, and the mean L2 norm also dropped sharply from 0.0322 to 0.00035.
Smaller weights mean more regularization. So higher data amplitude led to higher predicted ARM and observably stronger regularization on the weights.
Precisely. It's direct empirical evidence supporting the theory. BN automatically intensified the regularization in direct response to the increased amplitude of the input signals. It adjusted its own strictness.
That's really compelling. But you mentioned another aha moment from this experiment, looking at individual nodes.
Yes, this was fascinating. They didn't just look at the average ARM or average norms across the layer. They looked at the estimated ARM for each individual node in that 300-node hidden layer, shown in their figure 2.
And what did they see?
They saw that BN wasn't just applying a single uniform increase in R across all nodes. It was optimizing R to a potentially different suitable value for each node individually.
Wait, really? So node 1 might get a different regularization strength than node 150, even within the same layer, based on its own specific activation patterns.
That's what the visualization suggests. This is a huge difference compared to standard regularization methods like L1, L2 decay, where you set one single regularization strength that applies identically to all weights in the layer.
That is a huge distinction. VN is doing fine-grained, node-level dynamic regularization. That's way more sophisticated than just a global setting.
It really points to a much more nuanced, adaptive control mechanism than maybe people appreciated. A truly surprising and powerful finding.
Okay, experiment 1, strong validation for the constrained optimization theory, plus this bonus insight about node-level adaptation.
Yeah.
What about experiment 2? This one focused on the noise aspect, right? Signal versus noise ratio.
Correct. For the second experiment, they wanted to test the theory that BN makes regularization inversely proportional to the signal-to-noise ratio, SNR.
How do they manipulate SNR?
They took the clean MNIST dataset and deliberately injected additive noise. They added random noise drawn from a Gaussian distribution, just like in the theoretical setup. By varying the amount of noise added, they could directly control and perturb the input SNR.
So they created versions of MNIST ranging from pretty clean, high SNR to very noisy, low SNR.
Exactly. Then, just like before, they trained the MLP with BN on these different noisy data sets and measured the resulting mean L1 and L2 norms of the hidden layer weights to see how the regularization intensity changed.
And what was the prediction? Lower SNR, more noise, should lead to?
Lower SNR should lead to stronger regularization, meaning lower weight norms. BN should clamp down harder when the signal is obscured by noise.
It happened.
Again, the results, shown in Table 2, were definitive. As they decreased the SNR, for example, going from a clean SNR of 100 down to a very noisy SNR of 0.5, the mean L1 norm of the weights consistently decreased from 2.8823 to 0.3646.
And the L2 norm?
Same story. The mean L2 norm also decreased significantly from 0.1286 to 0.0163 as the SNR got worse.
So, more noise unequivocally led to smaller weights, indicating stronger regularization.
Yep. It definitively proves that BN makes the regularization parameter inversely proportional to SNR, just as the second theoretical perspective predicted. When noise increases relative to the signal, BN automatically tightens a regularization to prevent the model from learning the noise.
These experiments really seem to nail it then. Both perspectives, the optimization view and the noise view, are backed up by practical results. BN isn't just normalizing. It's actively, dynamically adjusting its own internal regularization based on data amplitude, data variance, and the signal-to-noise ratio.
It paints a picture of BN as a much more sophisticated and data-aware system than just a simple standardizer. It's performing intelligent adaptive control during training, #outro.
So let's wrap this up. What does this all really mean? We've taken a genuinely deep dive into batch normalization today, peeling back layers we didn't even know were there.
We really have. I think the main takeaway is this new theoretical understanding of BN's advantage. It's not just about faster training anymore. We now have strong evidence, both theoretical and empirical, that it automatically estimates and applies an appropriate regularization parameter.
Which is huge because that's normally such a manual, painful process.
Exactly. It solves, or at least significantly alleviates, a major hyperparameter tuning headache in deep learning.
And we saw this through two main lenses.
Right. First, framing BN as this constrained optimization problem, where the solution naturally leads to data-dependent regularization tuned by the gamma parameter based on activation strength.
And second,
Second, analyzing its behavior with noise, showing that its regularization effect is dynamically SNR-dependent, becoming stronger when noise is high relative to the signal, and adapting based on signal variance too.
and crucially, the experiments on MNest really brought this home. Seeing the weight norms change exactly as predicted in response to data scaling and noise injection, that makes it concrete.
It connects the abstract math to tangible network behavior.
So connecting this to the bigger picture, how should we think about BN now?
I think we need to see it as more than just a utility for faster convergence. It's a built-in adaptive mechanism for generalization. It's constantly making these intelligent micro-adjustments to regularization based on the data flowing through it.
Which makes models using it inherently more robust, less likely to overfit, without us having to explicitly micromanage that regularization aspect as much.
Precisely. It potentially reduces the burden on the practitioner significantly, moving towards models that are a bit more self-sufficient, more autonomously capable of handling varying data conditions.
And this research isn't the end of the story, is it? The paper mentioned future work.
Right. They specifically mentioned that analyzing this regularization auto-tuning effect in truly deep networks, beyond the shallow MLP they used for validation, is still an open and interesting research problem. There might be even more complex interactions happening in deeper architectures.
Always more to explore. Okay, so for you, the listener, thinking about all this, here's a final provocative thought to chew on. Considering that batch normalization is already, apparently, so cleverly auto-tuning its regularization based on data characteristics and noise levels, how might this deeper understanding influence how we design future AI systems? Could we leverage this kind of built-in adaptive intelligence even more explicitly? Could we build architectures that are even more robust, more effortlessly self-optimizing, minimizing the need for manual hyperparameter tuning and maximizing performance automatically? Imagine models that truly adapt their learning strategy on the fly to whatever data they encounter. What might that unlock? Lots to think about there. We hope this deep dive has given you some fascinating new perspectives on a technique many of us use every day. Thanks for joining us.